Hi, everybody. This video is going to address a little bit about what's called the collision theory, and then a description of and show you how to calculate some things from what's called a potential energy diagram. Okay. Now, I know you've already learned about the factors that affect the rate of a reaction. And a lot of those, those are things that are directly observable. Like you increase the concentration, the rate increases. You increase the temperature, the rate increases. You increase the surface area, the rate increases. This is the theory behind, like, well, why do we think that happens? And the basic premise is that, for substances to react, they have to bump into each other, they have to collide, they have to touch. And all of those factors, like increasing the concentration, well, that puts more molecules into, like a certain volume in a given time, and they're going to bump into each other more often because it's like a crowded room. You increase the temperature, particles are moving faster, they're going to bump into each other more often. You increase the surface area, and you have now like a powder that's reacting with the oxygen from the air. And if you increase the surface area, the oxygen can get to the reactants and create contact because there's additional surface area for them to have that contact. So this is like the theory behind like why we think a lot of those other factors affect the rate of a reaction. But just because substances have a collision, okay, just because they bump into each other, is not always going to mean that they end up having a chemical reaction. I'm having a little trouble getting the slide to advance, so give me a second here. There we go. So reasons why a collision could occur, but you don't get a product, okay? So the number one reason is they just don't hit in the right spot. I mean, molecules are three-dimensional. They have, there's a spot on molecule A and a spot on molecule B that have to make contact because that's the atoms that are going to be creating the new bond, sharing the electrons or transferring the electrons for the bonding to happen. So they have to hit in the right spot. To me, this is like you got the right puzzle pieces, but you have it turned wrong. So it just doesn't fit in correctly. And so you can't, put the piece into the puzzle unless you have the geometry right. You have it turned in the right way. So they call this like the molecular, the collision geometry of the molecules. Like they have to hit in the right spot for the bonding to possibly occur. And there's a lot of ways they can bump into each other and, not be hitting in the right spot. We're having a little bit of trouble here today with advancing. So let me get to the next one. There we go. Well, I got both of them. That's fine. Second, the second part of why you might have a collision but not get a product is they don't have enough kinetic energy. They're just not moving fast enough. Particles have to be moving fast enough to break old bonds and start forming the new bonds. If they don't run into each other with enough speed, they're not going to get up the hill to make this thing called an activated complex, which is where the old bonds start breaking and the new bonds start forming. And it's a really high energy, kind of unstable intermediate. And so they're just not going to be able to get up that hill. To me, I always describe this to students like you rolled the skee ball. You've all played skee ball, I hope. But you roll the skee ball and it goes partway up the ramp and it comes back to you because it just wasn't moving fast enough to complete and get into the scoring area. That's kind of what this is like. If the particles aren't moving fast enough, they're not going to be able to get up the hill to make the activated complex. They have to make the activated complex to turn into the product. And we're going to look at potential energy diagrams in a minute, and you'll kind of see what I mean by like get up the hill. The third reason why collisions might occur without resulting in a product is even if they hit in the right spot, okay, they hit in the right spot, they have enough energy, they make the activated complex. That activated complex is a real high energy intermediate, and it can literally go either way. That activated complex, the old bonds can break and the new ones can form, and you can end up getting a product. Or the new bonds that were just starting to, form, those can break apart and it can go back into what the reactants were. So any of these things could potentially make a collision not result in a product. It's amazing sometimes to me that chemical reactions even happen at all, and can often happen so quickly when there's all these different potentially things that could prevent them from, making a product. Now, what we usually do then is create a diagram of the reaction. Like here, here's the, oh, somehow I'm getting that. Here's the beginning of the reaction. Here's the end of the reaction. Now I don't like the way that yellow's showing up, so I'm going to switch colors here, okay? So you kind of have the beginning and you have the end of the reaction. And what this is, right here, this is the total amount of potential energy in kilojoules that the reactants possess. Over here, of course, corresponding to a number on the y-axis, this would be the total amount of energy in potential energy in kilojoules that the products possess, okay? Now you got to get in a chemical reaction from the reactants over to the product side, and you have to go over this hill to get there because basically, let me get some stuff out of the way here. I just want to erase these. But basically, you've got to get over the hill. You can't get from reactants to products without going over the hill. Because when the reactants start coming together and the old bonds start breaking and new bonds start forming, you get this thing called an activated complex. Some other words for that, I've seen it called a transition state. I've seen it called an intermediate. It is a very short-lived, unstable, sometimes referred to as a species because it's not really a stable substance. It's the old one breaking apart and the new one starting to form, and it's kind of this in-between state. It's very brief, but it's high energy. So the reactants have to be able to get up this hill, and that energy has to come from somewhere, and that's where they have to have enough kinetic energy to convert into potential to get up here and form the activated complex. Now, it can go back down and form the reactants. You could be back there, or the activated complex can turn into the products, okay? Now, every potential energy diagram, though, gives you information not just about the reactants, the activated complex, and the products, but some numbers that tell you something about that process. There is something called the activation energy, and I'm over here to the right side. The activation energy is the minimum amount that you need to get the reaction started and form that intermediate. So let me switch to another color here. I'll pick out like a green, okay? So you got to go from here up to there, and the difference in those numbers, like let's say this number was 500 and this one was 100. So the difference between the potential energy of the activated complex and the potential energy of the reactants, that's your activation energy. In this case, if it's 500 minus 100, it'd be 400 kilojoules. So they got to possess at least 400 kilojoules of kinetic energy so that they can even get all the way up that hill. Once they make the activated complex, and if they go on to make the products, it kind of depends where you end compared to where you started, okay? Here we see a net gain of potential energy. That change in the potential energy that happens during the chemical reaction, the net gain or net loss, that's called the enthalpy, sometimes referred to as the heat of a reaction, the delta H. Now, I know you just saw delta H in previous units, and those were heats that were gained or released in physical changes. Remember the heat of fusion, heat of crystallization. These would be heats that are gained or lost during a chemical change. Remember, these diagrams represent a chemical change. Now here, let's say this was 100 and it ended at 400. There's a net gain of 300 kilojoules. Since it was a net gain, it's an endothermic reaction. It gained energy through the process. Now, think to yourself, what would the reverse look like? I have that on a future slide, and you'll see that in a minute. Here's, the same endothermic reaction from the previous slide, but equations, you take the potential energy of the activated complex minus the potential energy of the reactants to get the energy of activation. And you take the potential energy of the products minus the potential energy of the reactants to get the enthalpy or the delta H. Now, in this case, remember, it's going to come out positive because the products have a higher number than the reactants. Anytime it's positive, it's going to be an endothermic change. So then you think, all right, what would an exothermic one look like? If it's got to have a negative delta H. So think to yourself what that might look like. And here's what it might look like. There's still a hill in the middle, but you end at a smaller number than where you started. So when you take the products minus the reactants, now you're going to take a smaller number minus a bigger number, you're going to get a negative answer. So for an exothermic change, the products end lower than where the reactants began. Now, there are some chemical reactions where these aren't that far apart, where the products are slightly higher, slightly lower. These products are a lot lower. So this one's going to release a lot of energy, and it's really going to get warm and give off, that energy. So now here's another concept that we're really going to get into, and I want to erase all my markings here. We're going to get into the fact that reactions are reversible. That's coming in some future lessons, okay? Just kind of switching colors here. But let me see. I need something darker. So if reactions are reversible, and that's going to be in the second half of this unit, that means that the products can go back over this hill and form the reactants. Okay, so if the products can go back over the hill and form the reactants, you end up with like a delta H that is the same numerical quantity, but with a different sign. Like this is an exothermic reaction. Let's say it released 300 kilojoules of heat. If you reverse this reaction and go back over to the reactants, there's going to be a net gain of 300 kilojoules of heat. So reversible reactions, they kind of just have the same delta H value, but it is a different sign, okay? And they do still have to go over the hill. One of the things I like to talk about if I'm here is which one of these reactions, the forward or the reverse, do you think is faster? Looking at this particular diagram, you can see that the hill this way is a lot lower than the hill going in the reverse. And so this one, the forward reaction, is going to have a faster rate than the reverse. We'll talk about reversible reactions and how when one of them's faster than the other, what that tells you about, which one's present in larger amounts at what we call equilibrium. So just kind of foreshadowing there, getting into a little bit of what you might see in, in the near future in some of the videos. So it says label the activation energy of the reverse reaction in the potential energy diagram above. The activation energy, the activation energy is going to be how much energy it needs to get up that hill. When you reverse a reaction, you still take the energy of the activated complex, but now you got to subtract the products because in reverse, the products become the reactants. So this would be the activation energy of the reverse reaction. And this is why it's slower. It has a bigger activation energy. It requires a lot more energy. So it's just going to be a lot slower. Going into what happens when there's a catalyst, because you learned about that at the beginning of this unit too, that adding a catalyst speeds up a chemical reaction. Now, when you add a catalyst, your reactants and your products, they don't change. You still have the exact same stoichiometry, the exact same balanced reaction. The catalyst just makes it happen faster. And even though they don't always understand how all catalysts work, I mean, that's a big area of study. They do know how some work. But one of the things that they think is that many catalysts will lower the Hill. They somehow stabilize the activated complex to make its potential energy lower. And so the activation energy with the catalyst, okay, is lower, which makes your energy requirements a lot less. And that means that more particles are going to be able to like have enough energy to get over the hill. Back in Unit 9, we had talked about like, what do you want to call it? That Maxwell-Boltzmann distribution, where like, here's the molecules temperature 1 and, you know, their kinetic energy. And then if you have a higher temperature, you know, the average starts moving out this way. And you can see like if there was a minimum energy requirement for this reaction to happen, like right here, if this is the number of kilojoules of energy this reaction needs to go, when you add the catalyst, okay, and you lower that energy of activation to a smaller number, you pick up a lot more molecules. Like before the catalyst, only these molecules could react. After the catalyst, these could. And you can see that at a higher temperature, you got a lot more particles that have enough energy. So raising the temperature gives them more kinetic energy, and adding a catalyst lowers the Hill. That combination, when you raise the temperature and you add a catalyst, really speeds up a reaction, okay? And you guys know the catalysts in your body are called enzymes. Some of them, they know how they work. Some of them, they don't. All right, so use the diagram to determine the following values. I tried to put some little numbers on this diagram, so hopefully you can see where they correspond. So the potential energy of the reactants, they're right here. So their potential energy is like 50 kilojoules, okay? The potential energy of the products, they're right here. So they are at 150 kilojoules, okay? And the activated complex is up here, so it's at 200 kilojoules. And all these other numbers are just using those and subtracting them to find, you know, the activation energy and the enthalpy in the forward and the reverse. So here, when you find the activation energy, it's the activated complex minus the reactants. So it's 200 minus 50. It takes 150 kilojoules to get up this hill, okay? And then the delta H is always the products minus the reactants. So over here is your delta H. There's a net gain, 150 minus 50. There's a net gain of 100 kilojoules. Now, if you reverse the reaction, that makes these the reactants and these the products. So then in reverse, you're going from here up the hill. So you take the activated complex minus the products, because they're now the reactants. And the hill is only 50. Well, that's supposed to be a 0 right there. And then in the reverse, remember the delta H, now you're taking the 50 minus the 150. You've reversed it. These are the products, those are the reactants. You should have the same number as before, but now just have, I'm having a little trouble getting my writing on there. Now just have an opposite sign. So that says negative 100. So in the forward reaction, you gain 100 kilojoules. That one's endothermic. and the reverse reaction, you lose 100 kilojoules, that one is going to be exothermic. Now, the substitute has a worksheet for you to try in class and practice these, and then a key to go over it. And then there's another worksheet. There's a front and a back, and that's going to be homework. And there will be a key, and that'll be checked after you complete that on your own at home. And you're just practicing, trying to learn these. I know the worksheet that you do for homework, it calls things species. And what they just mean is like, what's the formula for the activated complex? What's the formula for the reactants? They just call them species, okay? So don't let that deter you. But good luck. I hope that you can, get those work together and get those worksheets and homeworks, etc., completed, and learn about how to read these diagrams and get these important numbers from it. All right, good luck.